Okay, we are finding the geometric and algebraic multiplicity of a matrix. So, we have seen the matrix this 1 1 1 minus 1 minus 1 minus 1 0 0 0 0 1, and we have seen the roots of this matrix. We got the characteristics equation like this, and if we get the roots, we are getting the two distinct eigenvalues. So, this 0 is coming twice. So, that is why 0 is eigenvalue 0 is having algebraic multiplicity 2 and eigenvalue 1 is having algebraic multiplicity 1. Now, we will talk about geometric multiplicity. So, for that we need to find the set of eigenvector corresponding to this eigenvalue. So, let us try with the first one with the eigenvalue 0, and we need to find the eigenvectors, the set corresponding to the eigenvalue 0. So, eigenvectors for the eigenvalue lambda 1 equal to 0. So, how to get the eigenvectors corresponding to the eigenvalue 0? So, for that we need to get the all the non-zeros. So, this is x, all the non-zero vector x has that this is true. Now, lambda is 0. So, that means this is 0. So, we have to find the all the non-zero vector x for which a x equal to 0. So, what is a? A is nothing but 1 1 1, then the minus 1 0 minus 1 and 0 0 1. So, this into x 1 x 2 x 3, this is the 0 vector. So, if you simplify this, we will be getting like x, the equation like x 1 plus x 2 plus x 3 equal to 0, then minus x 1 minus x 2 minus x 3 equal to 0, and then x 3 equal to 0. So, this will give us x 1 plus x 2 equal to 0 and x 1 if we put this to be 0. So, we have x 1 plus, we have basically two equations, and x 1 plus x 2 equal to 0. So, we have option for x 3. So, if we choose say x 3 is 0, we have no option for x 3, sorry. So, now what are the values? Now, we can choose x 1 to be k or x 2 to be k. So, this will give us x 1 equal to minus x 2, which is say minus k, we choose x 2 to be k, and x 3 is 0. So, these are the, this is the set. Now, this will corresponding to the vector like so x 1 x 2 x 3, if we write it in a column way, this is nothing but if we take the k common. So, minus 1 1 0. So, this is the set of all possible eigen vector corresponding to the eigenvalue 0. So, now this is this set along with the 0. So, this set if k could be 0, these are all real numbers. So, this is the real field. So, we know this is a vector space and dimension of this space is called geometric multiplicity of this. So, this is generating by the one vector. So, dimension of this is 1. So, the geometric multiplicity of the eigenvalue 0 is 1. So, geometric multiplicity of the eigenvalue 0 is equal to 1, whereas algebraic multiplicity of 0 is 2, because 0 is coming twice in the root of the characteristics equations. Now, we can similarly we can find the which is this which is 1 and which is less than 2, which is the algebraic multiplicity of the this. Now, we try to find the geometric multiplicity of the eigen value lambda 2, which is nothing but 1. So, to get this we need to solve the homogeneous, we need to solve the equation A x equal to lambda 1 lambda 2 x lambda 2 x. So, this will give us lambda 2 is 1. So, we can just write 1 into x. So, if x is x 1 x 2 x 3. So, this will give us 1 minus 1 1 1, then minus 1 minus 1 minus 1 minus 1, then 0 0 1 minus 1 x 1 x 2 x 3. This is the corresponding a minus lambda x, a minus lambda I 0 0 0. So, this will give us the solution like, so if this is 0, this is 0. So, this will give us solution like x 2 plus x 3 equal to 0, and so this means x 2 equal to minus x 3, and if you solve it, we will be getting x 1 to be 2 x 2 minus x 3. So, if you just choose x 3, x 3 will be k, then x 2 will become minus k, and x 1 is becoming 2 of minus so x this is minus. So, 2 k minus k. So, this is also k. So, we have this x 1 x 2 x 3 is nothing but of this form. So, x 1 x 2 x 3, we take k common, it is 1 minus 1 1. So, this is generating the, so this is the corresponding, this is the all possible eigen vectors. So, every eigen vector is of this form. So, V of lambda 2 is nothing but so the dimension. So, this vector is generating the groove, generating the field. So, the dimension of lambda 2 is equal to 1, which is same as, this is the geometric multiplicity. So, geometric multiplicity, which is the geometric multiplicity of lambda 2, which is same as algebraic multiplicity here. Geometric multiplicity is less than equal to algebraic, less than equal to. So, here the equality is occurring here. Okay. So, these are the geometric and algebraic multiplicity of geometric multiplicity of a eigenvalue. Okay. So, now we will talk about some properties of eigenvalues. Say for example, if we have a real symmetric matrix. Okay. If we have a real symmetric matrix, then the eigenvalues are all real, and if we have a skew symmetric matrix, we want to see eigenvalues are either 0 or they are completely imaginary. So, let us try first one. So, the theorem is telling the eigenvalue of a real symmetric matrix. We know the symmetric matrix. Symmetric transpose of A is A are all real. So, eigenvalues of all reals. Eigenvalues of a real symmetric matrix. Suppose you have a real symmetric matrix A I j n cross n square matrix, where A I j's are real. So, that means, if you take the conjugate of this, then that is same as this. This is conjugate. and it is symmetric means transpose. If you take the transpose of this is same as A. This is an example of symmetric matrix. If we have 1 say minus 2 3, we have diagonal, we have nothing to do, but the value over here is same as value over here. So, if we have a say 4 over here, this has to be 4. So, value over here is same as value over here. If it is minus 5, we have a minus 5 over here. If you have a value over here say 9, this has to be 9. So, that means A I j equal to A j I. So, this is the for all I and j, then the matrix is called symmetric matrix. So, now this theorem is telling if you have a symmetric matrix and if all the coefficients are real, that means if the conjugate of A is same as this. So, conjugate means if you have a complex number A plus I b, then the conjugate of this is defined as A minus I b. But if b is 0, then it is called purely real, then A conjugate is same as this, and if A is 0, it is called purely imaginary. So, that is the thing. So, now we have to, so conjugate matrix means we take the conjugate matrix we defined as this, where we take the conjugate of each of these numbers. So, we are going to prove this, that real symmetric matrix will have real eigenvalues only. So, how to prove this? So, for this we take a so suppose lambda is the eigenvalue of the matrix A. So, that means A x, there is a non-zero vector x such that A x equal to lambda x, or we can say x 1, some non-zero vector x 1 not equal to 0 vector. So, what we do? We take the transpose of this. Now, before transpose, we take the conjugate. So, conjugate must be same, and then we take the transpose. So, if we take the conjugate, then it is nothing but A conjugate x 1 conjugate, then transpose equal to lambda conjugate x 1 conjugate transpose. Lambda is a scalar quantity. Okay. So, now this will give us, so transpose will revert this. So, this is x 1 conjugate transpose, and then lambda bar x 1 conjugate transpose. So, you have to simplify further. Okay. So, so now this this we can write as this x 1 conjugate A x 1 equal to lambda bar. We are just taking A both x 1 both side, lambda bar x 1 transpose conjugate x 1. So, if we further simplify this, we take this transpose, we have to be careful with this transpose and T bar and transpose. So, this is A x 1, because this associativity property is there, bar x 1 bar transpose x 1. Okay. So, let us just, so up to this is fine. Now, this is again lambda of x 1. So, lambda so this is again lambda of x 1 bar transpose x 1 equal to lambda bar x 1 bar transpose x 1. Now, this implies lambda equal to lambda bar, because okay, if you take this side, lambda minus lambda bar x 1 transpose x 1 equal to 0. Now, this is x 1 is non-zero. So, that means x 1 bar transpose x 1 is not equal to 0. So, this means this has to be 0, lambda is equal to lambda bar. So, this means lambda is this means lambda is real, purely real, no complex part, no imaginary part in it. So, this is the this is one of the theorem. If the eigenvalues are, if the matrix is symmetric, real symmetric matrix, then the corresponding all the eigenvalues are real. Now, this is true for Hamilton matrix also. So, we will define the Hamilton matrix, sorry, Hermitian matrix. Hermitian matrix. So, when we say matrix is Hermitian matrix, if A bar transpose equal to A, this is the definition of Hermitian matrix. So, then this is called then the matrix is called Hermitian matrix. Now, the way we prove in the last just now, the same technique will go, and we can say that all the eigenvalues of Hermitian matrix are real. All eigenvalues of Hermitian matrix are real. Okay. So, now we talk about real skew symmetric matrix, and we will see how their eigenvalues are. Let A is n by n matrix is a skew symmetric matrix, but the coefficients are real. It is real skew symmetric matrix. Skew symmetric means I will define that. Symmetric matrix. Then the eigenvalues are either purely imaginary or 0. Then the eigenvalues of A are purely imaginary, means there is no real part. So, like 2 plus 3 I, it is not purely imaginary. So, this part should not be there. So, that is the purely imaginary. So, eigenvalues are purely imaginary or 0. Okay. So, so this is how to, so what is a skew symmetric matrix? So, skew symmetric matrix is if A transpose equal to minus A, that is the skew symmetric matrix definition. That means, if A is A I j n cross n, then A I j must be equal to minus A j I, and this is true for all I and j starting from 1 to n. So, that is why the diagonal element where I is j is equal to I, diagonal element. So, A I I equal to minus A I I. So, that means 2 A I equal to 0. So, A I equal to 0. So, for any skew symmetric matrix, the diagonal elements are 0, and the off diagonal element, if we have a, so all the diagonal element will be zeros over here, and off diagonal element. So, if this is 2, this has to be minus 2, if this is minus 4, this has to be plus 4. So, that is the definition of skew symmetric matrix, and it is a real skew symmetric matrix. So, that means, this Aij's are real numbers. So, Aij's conjugate, if you take, it is Aij. So, that means, this conjugate of, so conjugate of conjugate matrix is same as this. So, this is the definition of real skew symmetric matrix. So, if you have a real skew symmetric matrix minus A, yes, if you have a real skew symmetric matrix, then we can show that the eigenvalues are either 0 or 1. Eigenvalues are either imaginary or pure. So, similar way we can argue that. Now, we will talk about orthogonal matrix. So, this proof we are not doing, this will be in the note, lecture note. So, now we talk about eigenvalues corresponding to the orthogonal matrix. So, suppose A is an orthogonal matrix. Orthogonal matrix. Orthogonal matrix means A at A transpose equal to identity. So, that means A transpose is an inverse of A. So, if we have a real orthogonal matrix, then the theorem is telling the eigenvalues of A has unit modulus. Unit modulus means mod of that eigenvalue, that means if lambda is eigenvalue, it is a complex number, maybe mod of this is 1, that is the unit modulus, had units mod modulus. Okay. So, this we have to prove. So, how to prove this? To prove this, suppose suppose lambda 1 is eigenvalue. So, and corresponding eigenvector is say x 1. So, we have this where lambda where x 1 is not equal to 0 and lambda 1 this. So, what we do? We take the transpose of this and we take the conjugate, then we take the transpose of this. Then this is nothing but A bar transpose A bar x 1 bar transpose, then so this similar thing we did in the last proof. So, let us erase this. So, this is orthogonal matrix, real orthogonal matrix. So, you have to use that property also here to achieve that. Okay. So, A bar transpose. So, if you take the transpose, it will give us x bar transpose and A bar is this is a real matrix. So, it is A. So, this is nothing but A transpose equal to, so x 1 is there. So, x 1 is already there, equal to lambda bar x 1 bar transpose. Okay. Now, we multiply both side by A x 1. So, this we love it. So, we multiply both side by A x 1 transpose this A x 1 equal to lambda bar x 1 transpose A x 1. Okay. So, now we take this together, A transpose A x 1 equal to this is A x 1 is nothing but lambda x 1. So, transpose lambda x 1. So, this lambda x 1, what we can do? So, this is identity matrix because this is the property of orthogonal matrix. So, this will give us x 1 transpose x 1, this is identity matrix, and this will give us lambda 1, we take this side. So, lambda 1, these are lambda or lambda 1, anyway lambda is lambda. So, lambda bar lambda x 1 bar transpose x 1. Okay. So, this will give us x 1 bar x 1 into 1 minus lambda bar lambda is equal to 0. Now, this is non-zero quantity. So, this implies lambda lambda bar equal to 1. Now, this implies mod of lambda equal to 1. So, if lambda is the complex number, so modulus is 1. So, it has unit modulus. Okay. So, this has unit modulus. So, we will talk about more on this, and in the next class we will define the diagonalization of the matrix. So, those we will discuss in the next class. Thank you.